Through this video, you will be introduced to the basic concepts of buckling, and how buckling analysis can be investigated in AquaSim. This is done through some simple case studies, where the aim is to present some basics of beam buckling. Concepts such as critical buckling load and buckling factor. Conduct a buckling analysis in AquaSim, and compare these results with a simple formula. Buckling is a phenomenon that commonly appears in slender structures that is exposed to compressive forces. Slender structures can be a beam or a plate. Buckling materializes as a rapid change in the shape, such as bulging or wrinkling. It may arise from loads which in themselves are not critical for the structural integrity, but the deformations may lead to unfavorable load transfer, which in turn can cause the load-bearing structural part to lose its load capacity. In this video, we will limit our focus to a simple beam structure. Let us look at the principles of buckling analysis in AquaSim. Buckling is possible to investigate on beam, membrane and membrane X. For beam components, both Morrison submerged and hydrodynamic is applicable. For membranes, buckling analysis is limited to shell and normal with bending stiffness. Explicit buckling analysis is quite easy to conduct in AquaSim. You apply a built-in tool that is found in the export menu. The buckling tool is available for both the analysis types normal and directional. Scroll down to the advanced section, until you find the buckling eigenperiod analysis. By selecting the three dots to the right, one enters the control window for buckling settings. Three interesting parameters are analysis type, amount of eigenvalues written to file, and shift value. Analysis type tells us if we want to conduct an eigenperiod analysis or a buckling analysis. Buckling analysis solves this equation. The result of the analysis is to solve the delta. The corresponding eigenvector is the buckling shape. Buckling shape may also be referred to as buckling mode. In this video, we stick to the word shape. The amount of buckling factors written to file must be a number between 0 or 7. If this parameter is equal to 3, then the 3 buckling factors closest to shift value is calculated. The buckling analysis is conducted by numerical method. The shift value enables a numerical search for buckling factors around this value. That is, it pinpoints an area in which one wishes to find buckling factors. Amplitude of the eigenvectors is more like a visual thing. It indicates how large the buckling shape should be visualized in AquaView. This is a unitless parameter and can be interpreted as an amplification factor for the buckling shape. Let us exemplify this by considering a beam that is exposed to compressive load. If the amplitude is equal to 5, the buckling shape may look like this. But if we increase this to 20, the shape will become more exaggerated. Having conducted the buckling analysis, some additional files will be generated. If you have chosen to set amount of eigenvalues written to file equal to 6, you will get 6 additional files. The first file, buckle1, includes the results for the buckling factor that is closest to shift value. The buckle2 file contains results for buckling factor second closest to shift value, and so on. Please note that each step in the analysis is considered separately, such that you must evaluate each step. Let's proceed with some practical examples. Through this case study, we should investigate buckling of a Euler beam. Consider a straight prismatic beam. It is pinned in both ends. Euler's formula provides a theoretical prediction of the critical load at which buckling occurs. When the applied load exceeds the critical load, the beam becomes unstable in the lateral direction and buckling initiates. The critical buckling load, PCR, can be described as this. E is the modulus of elasticity, I is the moment of inertia for the cross-section, K is beam effective length factor, and L is the effective length of the beam. The effective length factor K depends on the boundary conditions of the beam, whether it is free fixed, pinned, fixed pinned, and so on. For example, if the beam that is pinned, K is equal to 1, while for other boundary conditions K will be different. The beam that we just saw has the following particulars. It is exposed to a compressive load of 10,000 Newton. And by applying the Euler formula, we get a critical buckling load of 1727 kN. Let us go to AquaEdit and where we have modeled the same beam. The Euler beam is modeled as a beam component, with the load formulation Morrison submerged. If we enter the Edit Beam window, we see that the cross-section is 1 meter by 0.1 meter. Looking at the boundary conditions, the lower node is free to rotate about X and Y axis. Otherwise, it is restrained. The top node is free to move in Z direction. At the same top node, we have a point load. The point load is pointing in negative Z direction. This will correspond to a compressive force. If we remove the cross-section view, we see that the beam is built up by a fairly number of elements. This is to make the buckling shape smoother. Go to the Export menu and open the Buckling Analysis window. The chosen analysis type is buckling. Amount of eigenvalues written to file is 6. This will generate 6 buckling files, with 6 buckling factors. The rest of the parameters are left according to default settings. Select OK. Export and start the analysis. Let us have a look at the first file, the buckle 1. This file looks like an ordinary result file from AquaSim. The difference is that it contains only results-related buckling. If we zoom in here, and start the playback, we can see how the beam deforms. This is the first buckling shape. Relevant result from a buckling analysis is the buckling factor. The buckling factor is found from the result menu. AquaSim found a buckling factor of approximately 172. The buckling factor is the critical buckling load, PCR, divided by the load in the system. From the simple calculations, we found that the critical buckling load was approximately 1727 kN. When the system was exposed to a compressive force of 10 kN, this will give a buckling factor of 172.7. So, we can see that this simple case compares very well. The other files contain other buckling shapes. The buckle 2 contain the next buckling shape. And the third looks like this. The same exercise has been done again in AquaSim, only this time with the use of shell. The model is built up with membrane panels of 0.1 meter, and thickness of 0.1 meters. This will result in a model with 1000 panels, fairly large amount, but our system is quite simple so it will not affect computational efforts much. The total applied load and boundary conditions are the same as the previous case. Both ends are pinned. We run the same buckling analysis, with the exact same setup. When the analysis is finished, we open the buckle 1 file and study the buckling shape. This looks quite similar as for the beam case. Looking at the buckling factor, we find that this is 171.93. This aligns very well with the previous results. So, this was an introduction to buckling analysis in AquaSim. All files presented here, and more, is available online at our website. Visit aquasim.no for more videos.